Every great journey in history had a way back. This one doesn't. The moment you leave the solar system, you leave behind every human being who ever lived, every safety net ever built, every chance of rescue forever. And we can't even get there yet. Nobody who leaves the solar system will ever come back. If you are curious about these mysteries, make sure to subscribe to this channel and give a thumbs up. Now let's begin this journey. So, where does the solar system actually end? And that sounds like a simple question, right? But it turns out the answer depends entirely on what you mean by end. And this is where things start to get genuinely wild. Most people, when they picture the solar system, imagine the sun in the middle, the 8 planets circling around it, and then just empty space. Maybe Pluto floating somewhere out at the edge, but that picture is wrong. Not a little wrong, wildly, enormously, almost comically wrong. The truth is that our solar system is not just the planets. It is a vast, layered structure, like a cosmic onion with several very different shells, and each layer reveals just how much farther we have to go before we are truly outside this system. Let us peel those layers back one by one, and as we do, I want you to hold on to something. Every time you think we have reached the edge, we have not even close. The first layer most people know is the realm of the planets. Starting from the Sun, you travel out through Mercury, Venus, Earth, Mars, then the asteroid belt, then the 4 gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. Neptune orbits the Sun at about 30 astronomical units. 1 astronomical unit is the average distance between the Earth and the Sun, roughly 93 million miles. So Neptune is about 30 times that. If the Sun were the size of a basketball and you put it in the center of a football field, Earth would be a tiny marble sitting about 28 feet away. Neptune would be a pea sitting roughly 850 feet away near the far end of the parking lot. Already the scale is staggering, and we have barely started. Beyond Neptune lies the Kuiper Belt. Think of it as a wide, donut-shaped ring of icy objects, rocks, and small frozen worlds, stretching from about 30 astronomical units all the way out to roughly 50. Pluto lives here. So does a whole neighborhood of similar icy bodies called Kuiper Belt objects. For a long time, scientists thought this was the outer edge of things. It was not. Here is the first moment where the scale starts doing something to your chest. Beyond the Kuiper Belt is a region called the scattered disk, and then beyond that, at distances that can reach hundreds of astronomical units, things begin to get truly strange and empty. The sun's light, which reaches Earth in just over 8 minutes, takes hours and hours to reach the outer edges of this region. The sun, which rules our sky, barely looks like a bright star from out there. You would need sunglasses on Earth, but out there, you would need a telescope just to find it. And even out there, past the scattered disk, past the known frontier of the known planets and icy worlds, we are still not close to the true edge of the solar system, not even remotely. Because what waits beyond all of that is something that most people have never heard of, something so large, so distant, and so mysterious that astronomers have never actually seen it directly. They know it is there because of the clues it leaves behind. They know it is there because of the comets. We are talking about the Oort Cloud. And the Oort Cloud is where the story gets absolutely mind-bending. Right here, before we go deeper down this rabbit hole, I want to take a moment and say something genuinely from the heart. If this kind of content speaks to you, existence back in 1950, this structure is believed to be a vast, spherical shell of icy bodies surrounding the entire solar system. Not a ring like the Kuiper Belt, a sphere. A complete bubble of loosely bound chunks of rock and ice orbiting the sun at mind-bending distances. How far out does it reach? Estimates suggest the inner edge of the Oort Cloud begins at roughly 2,000 astronomical units from the Sun, 2,000 times the Earth-Sun distance. That is already so far that the numbers almost stop meaning anything. But the outer edge, The outer edge of the Oort Cloud is thought to extend somewhere between 50,000 and 100,000 astronomical units from the Sun. At 100,000 astronomical units, you are looking at a distance of roughly 1.5 to 2 light-years from our star. Let that settle in for a second. 1 light-year is the distance light travels in an entire year. Light moves at about 186,000 miles per second. In 1 year, it covers about 5.9 trillion miles. The outer edge of our solar system's gravitational reach may extend nearly 2 light-years from the Sun. Voyager 1, the most distant object humanity has ever launched, the probe that has been flying for nearly 5 decades at tens of thousands of miles per hour, is currently sitting at about 171 astronomical units from the Sun. The outer Oort Cloud begins at 2000. Voyager 1 has not even reached the beginning of the outer edge of our own solar system's gravitational influence. Think about that. 50 years of flight, 38,000 miles per hour, and we have covered less than 1/10 of the distance to the start of the Oort Cloud. According to current estimates, Voyager 1 will not even enter the Oort Cloud for roughly 300 years. And it will not exit the Oort Cloud, emerging on the other side into truly open interstellar space for approximately 30,000 years. 30,000 years. When Voyager 1 finally clears our solar system completely, human civilization as we know it will be ancient history. Agriculture has only been around for about 12,000 years. The pyramids are only 4,500 years old. 30,000 years from now, who knows what humanity will look like if we are even still here? So we left off at the edge of the Oort Cloud, that enormous invisible shell of icy debris wrapping itself around everything we call home. But before we can truly understand why leaving the solar system is essentially a one-way journey into impossibility, we need to talk about something even closer. Something Voyager 1 is passing through right now at this very moment as it drifts further and further from the Sun. We need to talk about the heliosphere. And we need to talk about what happens when you cross its outermost wall. Picture the Sun as a giant, living bonfire. Not just burning, but constantly exhaling. Every single second, the Sun blasts out a stream of charged particles, mostly electrons and protons, at speeds ranging from roughly 300 to 800 kilometers per second. This relentless outward breath is called the solar wind, and it does not just stay near the Sun, it pushes outward in every direction, filling an enormous bubble of space with its magnetic field and its particles. That bubble is the heliosphere. It is, in the most literal sense, the atmosphere of the Sun, stretched out across billions of miles of space, and it wraps around everything in our solar system like an invisible force field. Now here is where it gets layered and genuinely fascinating. The heliosphere is not a simple, clean balloon. It has structure. It has zones within zones, each one telling a different story about the battle being waged at the frontier between our Sun's influence and the broader galaxy. The innermost region is where the solar wind flows freely, unimpeded, rushing outward at supersonic speeds. Think of it like a river moving fast and smooth before it hits a waterfall. But eventually, far out past the orbit of Neptune, that river hits something. It slams into the pressure of the interstellar medium, the thin gas and plasma that fills the space between stars throughout the Milky Way. When the solar wind collides with that outside pressure, it slows down suddenly and dramatically. This collision zone is called the termination shock. Voyager 1 crossed it back in December of 2004 at a distance of about 94 astronomical units from the Sun. That was a historic moment. Scientists had theorized this boundary for decades, and suddenly, for the first time ever, a human-made object was sending back real, live data from that exact crossing point. Beyond the termination shock lies a region called the heliosheath. This is where the solar wind, now slowed and compressed, piles up and churns like turbulent water behind a dam. It is a strange, messy, in-between zone where the sun's energy is gradually losing its grip on the surrounding space. The heliosheath extends for dozens of astronomical units, and it is a scientifically fascinating place. Voyager 1 spent years crossing it, collecting data the entire time, overturning predictions that scientists had held for years. Then finally, there is the outermost wall, the boundary where the solar wind and the interstellar medium reach a kind of standoff, pushing against each other with equal force. This is the Heliopause, and this, for most practical purposes, is what scientists call the edge of the solar wind's direct influence. On August 25, 2012, Voyager 1 crossed the Heliopause. It became the first human-made object in history to enter interstellar space. At the time, it was sitting at about 121 astronomical units from the Sun. That was one of the most extraordinary moments in the entire history of space exploration. Engineers and scientists at NASA's Jet Propulsion Laboratory had been waiting for that crossing for decades, and the data Voyager 1 sent back was stunning. On one side of the Heliopause, it was measuring the particles and magnetic fields carried outward by the Sun. The moment it crossed, the particle counts shifted. The type of radiation changed. The magnetic field direction changed. It was like walking through a doorway from one room into a completely different one. The universe beyond that door was filled not with solar particles, but with the ancient, diffuse material of the interstellar medium itself, material forged in the hearts of stars that died billions of years ago. Material that is, in a very real and poetic sense, the raw fabric of the galaxy. Voyager 2 followed a different path and crossed the Heliopause in November of 2018, giving scientists a second data point from a completely different direction. And the data from both crossings confirmed something remarkable. The interstellar medium is not uniform. It is structured, complex, and full of surprises. Our heliosphere, it turns out, is not perfectly spherical. It is more elongated on the side, facing the direction the Sun travels through the galaxy, and compressed on the other side. The universe does not do simple shapes. Now, at this point, you might be thinking, okay, so Voyager 1 is already in interstellar space. Mission accomplished, right? We have left the solar system. But here is where we need to pause and be precise, because this is one of the most common misunderstandings in all of popular science. Crossing the Heliopause does not mean leaving the solar system, it means leaving the heliosphere. Those are two very different things. Think of it this way. Imagine the Sun's gravitational influence as one thing, and the Sun's wind and magnetic bubble as another. The Heliopause is the edge of the bubble, but the Sun's gravity, its gravitational reach extends far, far beyond the Heliopause. The Oort Cloud, which we talked about in Part 1, sits entirely outside the Heliopause, yet every single object in the Oort Cloud is still gravitationally bound to the Sun. Those icy bodies, orbiting at distances of tens of thousands of astronomical units, are still technically part of our solar system. They are still going around our star, even if each orbit takes millions of years to complete. So Voyager 1 is in interstellar space in the sense that it is outside the Sun's protective magnetic bubble, but it is nowhere near being free of the Sun's gravitational family. Not by a factor of hundreds, it is a bit like stepping out of your house and into your front yard. You are outside the building, but you are still very much on the property. Speaking of distances and journeys that feel impossibly long, here is something that might hit close to home. If you have ever wondered what it actually feels like to wrap your head around the distance between our Sun and the nearest star, I made a video that goes deep into exactly that challenge. It is called "This is Why We Will Never Reach Our Next Star," and it pairs perfectly with what we are talking about right now. The link is on the card above, but let us get back to Voyager 1, because the story of this spacecraft is not just a story about distance. It is a story about time, endurance, and the fragility of everything we send into the dark. Here is something that should genuinely take your breath away. Voyager 1 was designed to operate for 4 years, just 4 years. It was built to swing past Jupiter and Saturn, study their moons, and then drift away into space. Nobody was expecting it to still be functioning almost 50 years later. The fact that it is still alive, still sending back data, is one of the greatest engineering achievements in human history. And yet the clock is ticking. Voyager 1 is powered by a device called a radioisotope thermoelectric generator, or RTG. Think of it as a nuclear battery. It uses the heat produced by the radioactive decay of plutonium-238 to generate electricity. When the probe launched in September of 1977, its RTG was producing about 470 watts of power. Not much. About enough to run a few light bulbs, but enough to keep the instruments alive and the radio transmitter broadcasting back to Earth. Over time, the plutonium decays and the power output drops steadily. By the mid-2000s, power had dropped enough that NASA had to start shutting off instruments to keep the most critical systems alive. By the time you are watching this video, Voyager 1 is producing somewhere in the range of just a few tens of watts of usable power. Scientists estimate that within the next few years, the power will drop below the minimum needed to operate any of its remaining instruments, and the probe will go silent forever. When that happens, Voyager 1 will still be out there. It will not stop moving. There is essentially nothing in interstellar space to slow it down. No friction, no drag, almost no gravitational interference from nearby objects. It will just keep drifting outward in silence, carrying a golden record filled with the sights and sounds of Earth, a message in a bottle thrown into an ocean so vast that the odds of it ever being found are nearly incomprehensible. But nearly incomprehensible is not the same as zero, and that distinction matters. What Voyager 1 has taught us since its crossing into interstellar space is enormously valuable. Before this mission, our understanding of the outer heliosphere was almost entirely theoretical. Scientists had equations and models, but no actual data from beyond the heliopause. Now we have it. And the data is already challenging long-held assumptions. For example, the density of plasma in interstellar space near the heliopause was found to be higher than many models predicted. The structure of the magnetic field at the boundary was more complex than expected, and the distribution of cosmic rays, those high-energy particles streaming in from deep space, changed in ways that gave scientists new insights into the environment between stars. Cosmic rays are particularly interesting in this context. Deep inside the heliosphere, the Sun's magnetic field acts as a partial shield against these particles. As Voyager 1 crossed the heliopause, its instruments detected a dramatic increase in galactic cosmic rays flooding in from the broader galaxy, and a corresponding drop in the lower energy particles associated with the Sun. It was a clear, sharp, unambiguous signal that the probe had moved from one environment into another. The Sun can no longer protect it, and if humans were ever on board that craft, that spike in radiation would be a serious problem. But we will get to the question of human survival beyond the heliopause in a later part of this script. For now, just sit with this. The only direct measurements we have of interstellar space near our solar system come from a probe the size of a compact car, built with technology from the early 1970s, running on less power than a household light bulb, communicating with Earth through a radio signal so faint that it would be completely overwhelmed by the static of a cell phone. And yet, that signal travels across nearly 16 billion miles of emptiness and is picked up by the enormous antennas of NASA's Deep Space Network, spread across 3 continents on Earth. It takes that signal almost 24 hours to make the journey. By late 2026, it will take a full day for any message to reach the probe, and another full day for a reply to come back. That 48-hour round-trip communication time is itself a statement about how far we have come, and how far we have yet to go. Because remember, all of this, the heliopause, the interstellar medium, the fading heartbeat of a 50-year-old probe, This is still inside our cosmic neighborhood. The nearest star, Proxima Centauri, sits at 4.24 light-years from the Sun. That is about 266,000 astronomical units. Voyager 1, after half a century of flight, has covered about 171 astronomical units. At its current pace, it would take roughly 73,000 years to reach Proxima Centauri if it were even headed that way, which it is not. 73,000 years. Think about what our species has accomplished in the last 73,000 years. We went from surviving a near-extinction event to building cities, writing poetry, composing symphonies, splitting atoms, and launching spacecraft. And yet that entire span of time represents one trip, at our best current speed, to the nearest star. The universe is not trying to be cruel. It is not putting up walls to keep us in. It simply operates at scales that have nothing to do with human time or human ambition. And that is both the most humbling and the most awe-inspiring thought you can hold in your head on a Tuesday afternoon. Let us talk about speed, real speed. Not the kind of speed you feel when a car merges onto a highway or even when a fighter jet rips across the sky. We are talking about the kind of speed that breaks your intuition completely, the kind that makes your brain quietly shut down its expectations and just surrender to the mathematics. Because here is the problem at the very heart of this whole conversation. Even if we somehow solved every other challenge, the funding, the materials, the life support, the navigation, we would still be standing in front of a wall so thick and so immovable that the laws of the universe themselves built it. That wall is the speed of light. And the story of why we cannot break through it is one of the most profound and beautiful stories in all of science. Let us start where most people start, with our fastest spacecraft. As of December 24th, 2024, the record for the fastest human-made object belongs to the Parker Solar Probe. NASA launched it in 2018 specifically to study the Sun up close, swooping in and out of the solar corona on a series of increasingly tight orbits. During its closest pass to the Sun on that Christmas Eve in 2024, it reached a speed officially recorded by the Guinness World Records at 192.22 kilometers per second. In miles per hour, that is 430,000. 430,000 miles per hour. That number sounds extraordinary, and in human terms, it genuinely is. At that pace, you could travel from New York to Los Angeles in under 30 seconds. You could circle the entire Earth in under a minute. It is, without question, the fastest anything built by human hands has ever moved in the entire history of our species. And against the cosmos, it is a whisper. The speed of light is approximately 299,792 kilometers per second. The Parker Solar Probe, our fastest achievement, our greatest triumph of speed, travels at about 192 kilometers per second. That is roughly 0.064% of the speed of light. Not 6%, not even 1%, 6/100ths of 1%. If the speed of light were a race across the entire United States from coast to coast, the Parker Solar Probe would be sitting about a mile from the starting line. Now the Parker Solar Probe is not actually heading anywhere near the stars. It is looping around the Sun in a tight elliptical orbit, using Venus's gravity to tighten its path with each pass. Those extreme speeds only occur at the closest point of each orbit, during what is called perihelion, where the Sun's gravity slings it forward with incredible force. The moment it swings back outward, it slows dramatically. If you actually wanted to send a probe to another star and maintain a meaningful fraction of that record speed over the entire journey, you would need something far beyond what we currently have. And that brings us face to face with the most fundamental barrier of all, not engineering, not budget, not political will. The barrier is physics, Specifically, it is a set of ideas that a young patent clerk in Switzerland published in a single astonishing year, 1905. Albert Einstein's theory of special relativity rewrote everything we thought we knew about motion, time, and mass. Before Einstein, the universe ran on Newtonian physics. In that world, speed was simple. You push something, it goes faster. You keep pushing, it keeps going faster. If you wanted to double someone's speed, you just doubled the energy. The math was clean, intuitive, and, for the ranges of speed that humans deal with in everyday life, almost perfectly accurate. But Einstein showed that this picture breaks down completely as you approach the speed of light. And it breaks down in a way that is not just inconvenient, it is absolute. Here is the core idea, explained as simply as possible. In our universe, the speed of light in a vacuum, approximately 186,000 miles per second, is a universal constant. It does not matter how you measure it or how fast you yourself are moving. Whether you are standing still on Earth or hurtling through space at half the speed of light, if you measure the speed of a beam of light passing you, you will always get the same answer. This is not an approximation. It has been tested millions of times with extraordinary precision, and it never fails. The speed of light is the same for all observers, always. That one simple fact leads to a cascade of consequences that are almost impossible to believe, but are absolutely rigorously true. The first consequence is that as an object moves faster, truly fast, a significant fraction of light speed, time itself begins to behave differently for it. A clock on a fast-moving spacecraft ticks more slowly than a clock back on Earth, not because of some mechanical glitch, but because time genuinely passes at a different rate in a moving frame of reference. This effect is called time dilation. At low speeds, the difference is so tiny it is almost unmeasurable, but as you approach the speed of light, the effect becomes dramatic. At 90% of light speed, time for the traveler passes at roughly 44% of the rate experienced by a stationary observer. At 99% of light speed, the traveler's clock runs at only about 14% of the normal rate, push to 99.99%, and the traveler's time slows to less than 1% of what you experience watching from Earth. The closer you get, the more extreme the slowing becomes, approaching zero as speed approaches light. Now you might be thinking, wait, is not that a good thing? If time slows for the traveler, could they not make the journey to a distant star in a reasonable amount of time from their perspective? And the honest answer is, theoretically, yes. In principle, a spacecraft traveling close enough to light speed could cross enormous distances in what feels like months or years to the crew. But this does not make interstellar travel practical or possible with any technology we can conceive of. And here is why. The second consequence of special relativity is that as an object moves faster, it effectively becomes harder and harder to accelerate further. In physics, we describe this as an increase in relativistic mass. As your speed climbs toward the speed of light, the amount of energy needed to push you just a little bit faster does not increase linearly. It increases dramatically toward infinity. Think of it this way. Imagine pushing a shopping cart. At rest, it takes a certain amount of effort to get it moving. Push it to half the speed of light, and you have done something extraordinary. But to get it from half light speed to 90% light speed, you need far more than just a little extra push. And from 90% to 99%? More still, vastly more. And from 99% to 100%? An infinite amount of energy, literally infinite. This means that accelerating any object with mass, any object at all, to exactly the speed of light is physically impossible. Not difficult, not expensive, not a future engineering problem. Impossible. The mathematics gives you an infinite energy requirement, and the universe has no source of infinite energy. Only particles with no mass at all, like photons of light, can travel at that speed. Everything else is forever locked below it. Now let us take this to the practical level and make it viscerally real. Suppose we built the most advanced spacecraft our imagination can produce, Suppose we managed to achieve just 10% of the speed of light, which would be roughly 30,000 kilometers per second. That would be an achievement so far beyond anything we can currently do that it almost defies imagination. The Parker Solar Probe travels at about 192 kilometers per second. We would need to go roughly 156 times faster than that. And at 10% light speed, how long would it take to reach Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away? About 42 years. 4 decades of travel, one way. No stopping, no slowing down to look around, just flying. And that assumes you somehow solved every other problem. The fuel to get to that speed, the fuel to slow down on the other end, the radiation shielding, the life support, the psychological endurance of the crew, the communication delays back to Earth. At 20% of light speed, about 21 years, one way. At 50%, about 8.5 years, still one way. And these numbers assume we can reach those speeds in the first place, which as of right now, we cannot remotely approach. Our current best, the Parker Solar Probe at perihelion, travels at about 0.064% of light speed. To get to 10% of light speed would require increasing our spacecraft velocity by a factor of roughly 160, and the energy required to do that does not scale linearly. Because of the relativistic effects we just described, the energy climbs steeply, almost savagely, the faster you push. Here is one more way to look at it that might make the scale land differently. The Sun puts out an almost incomprehensible amount of energy every single second, roughly 3.8 times 10 to the 26th watts. That is 3.8 followed by 26 zeros in watts every second. It is the combined nuclear furnace of a star burning through about 600 million tons of hydrogen every single second. If you could somehow harness the entire energy output of the Sun for an entire year and direct every single joule of it into accelerating a spacecraft, you still could not push a reasonably sized ship to the speed of light. The math simply does not allow it. This is not a funding problem. It is not an engineering gap that better materials will close. It is a structural feature of reality. The universe comes with a speed limit built directly into its foundations, and that limit is the speed of light. Every other speed is possible in principle. That one is not. But here is where something extraordinary and quietly beautiful enters the picture. The same theory that closes the door on breaking the speed of light also opens windows we never expected to find. Time dilation, the very effect that seems like a footnote at first glance, is actually one of the most mind-bending gifts that physics has ever handed us. Because while you cannot travel faster than light, you can, in principle, cheat time itself. A traveler moving near light speed ages more slowly than the universe around them. From their perspective, journeys that take thousands of years in the outside universe might pass in just a few decades of subjective time on board. This is not magic. This is not science fiction. This is a mathematically confirmed, experimentally verified prediction of special relativity. We have already measured time dilation directly. Atomic clocks aboard fast-moving satellites run at slightly different rates than identical clocks on the ground. GPS satellites actually have to correct for both special relativistic effects from their speed and general relativistic effects from their altitude in order to stay accurate. Without those corrections, GPS would drift by kilometers per day. Time dilation is not theoretical. It is baked into the technology you use to navigate traffic. So yes, in principle, a human being could board a spacecraft, travel near the speed of light, reach a star dozens of light years away in what feels like just a few years of their personal time, and arrive at their destination. The universe around them, however, would have aged by decades or centuries during that journey. Their friends, their families, their entire civilization, gone, replaced by generations they never knew. The journey would be a one-way ticket, not just in terms of distance, but in terms of time itself. You could leave Earth in 2026 and return, if you returned at all, to a world so far in the future that every face you ever loved has been dust for generations. That is what the physics actually says. And no amount of engineering, no amount of determination changes that fundamental truth. The universe is not hostile to us. It is simply vast on scales that treat human lifetimes as rounding errors. So now we know the distance, we know the speed limit, we know what the physics of our universe has to say about the whole enterprise of trying to cross the void between stars. But here is the thing about human beings: we do not give up easily. Even when the universe posts a sign that says impossible, we tend to squint at it, tilt our heads, and start asking questions. And over the decades, some of the most brilliant minds on this planet have looked directly at the interstellar travel problem and said, okay, the easy ways are out, let us think harder. The result of that thinking is a collection of ideas that range from genuinely promising to breathtakingly creative to completely impractical with any foreseeable technology to almost poetically absurd. And going through them one by one tells you something profound, not just about the challenge of leaving the solar system, but about the nature of human ambition itself. So let us walk through the main proposals that physicists and engineers have actually put serious thought into, starting with the ones grounded closest to reality and moving outward into more speculative territory. The first serious concept worth understanding is nuclear pulse propulsion, and this one has a genuinely fascinating and slightly alarming history. Back in the late 1950s and into the 1960s, a group of physicists and engineers at General Atomics in San Diego worked on something called Project Orion. The basic idea was, in retrospect, almost comically audacious. You build a massive spacecraft, behind it you attach a heavy steel plate. You eject small nuclear bombs out of the back of the craft one at a time and detonate them just behind that plate. Each explosion delivers an enormous shockwave that kicks the plate and therefore the entire spacecraft forward. You do this repeatedly, thousands of times, using each detonation as a pulse of thrust. The numbers, in principle, were genuinely impressive. Physicists like Freeman Dyson, one of the most creative scientific minds of the 20th century, calculated that a nuclear pulse spacecraft of the Orion design could potentially reach speeds on the order of 3 to 5% of the speed of light. That would translate to a travel time to Proxima Centauri of roughly 100 years or so. Not ideal for the crew aboard, but not the geological timescale of Voyager 1 either. An uncrewed version could conceivably make it in something approaching a human lifetime. Project Orion was eventually shut down, not because the physics was wrong, but because of politics and law. The 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in space, effectively killed it. And beyond the treaty, the environmental and safety concerns around detonating thousands of atomic bombs near Earth were, understandably, substantial. Wernher von Braun, the rocket engineer who played a central role in the American space program, actually supported the project. But the world decided that launching a spacecraft by repeatedly exploding nuclear bombs behind it was perhaps not the wisest way forward. Building on the Orion legacy, the British Interplanetary Society proposed a more sophisticated design in the 1970s called Project Daedalus. Rather than fission bombs, Daedalus would use nuclear fusion, specifically the same process that powers the Sun. Tiny pellets of deuterium and helium-3 would be ignited by electron beams, producing controlled fusion pulses that would drive the spacecraft forward. The design called for a two-stage vehicle that would accelerate to about 12% of the speed of light. At that velocity, it could reach Barnard's star, a red dwarf about 6 light-years away, in roughly 50 years. Project Icarus, started in 2009 by members of the British Interplanetary Society and the Tau Zero Foundation, revisited and updated the Daedalus design, incorporating decades of additional fusion research. The project explored multiple fusion drive concepts and produced an enormous body of technical papers, though it never produced a flight-ready design. The core problem shared by all of these nuclear propulsion concepts is profound and practical. We have not yet achieved sustained, controlled nuclear fusion here on Earth, despite decades of effort and billions of dollars spent in pursuit of that goal. Fusion is notoriously difficult to sustain. Getting more energy out of a fusion reaction than you put in, what scientists call ignition, was only recently achieved at the National Ignition Facility in California in December of 2022, for the first time in history. But achieving it in a controlled, repeatable, scalable way, and then engineering that process into a spacecraft engine, that is a different mountain entirely. A fusion-powered rocket remains firmly in the realm of future technology. Possible in principle, realizable in practice? Not yet, and not soon. Then there is the concept that probably got the most public attention in recent years. In 2016, physicist Stephen Hawking and Russian billionaire Yuri Milner stood before cameras at the top of One World Trade Center in New York City and announced something extraordinary. They called it Breakthrough Starshot, and the ambition was staggering. The plan was to develop tiny spacecraft barely larger than a postage stamp attached to gossamer-thin lightsails. A ground-based array of powerful lasers collectively producing roughly 100 gigawatts of energy would fire a sustained beam at these sails as the tiny probes launched. The radiation pressure of the laser light pushing on the sail would accelerate the craft to roughly 20% of the speed of light. At that pace, the tiny probes could reach the Alpha Centauri system in about 20 years. The project was announced with $100 million pledged toward a proof of concept. The idea, stripped down to its essence, is elegant. Light sails work on a real, verified principle. Sunlight carries momentum, reflect it off a mirror, and the mirror gets a tiny push. Do that with a powerful enough beam of focused laser light, and the push becomes significant. Solar sails have already been tested in space. The Japanese Icaros mission in 2010 became the first spacecraft to demonstrate successful interplanetary travel using solar sail propulsion. NASA's NEA Scout mission also carried a solar sail. The physics is real, but Breakthrough Starshot ran into wall after wall of engineering nightmares. Producing 100 gigawatts of laser power coherently from the ground requires a laser array larger than anything ever built by a factor of thousands. Keeping the sail centered in the beam as it accelerates away at 20% of light speed within the first few minutes is an almost incomprehensible pointing and control challenge. The sail itself, which would need to be extraordinarily thin and reflective, must survive the crushing intensity of a 100-gigawatt laser without vaporizing. And once the tiny probes arrive at Alpha Centauri, they have no way to slow down. They would zip through the system at 20% of light speed, which means they have only a few hours in the vicinity of any planets or stars before they have screamed past and are gone forever. Data transmission back to Earth from 4 light-years away from a device barely bigger than a postage stamp is itself a gargantuan engineering puzzle. Breakthrough Starshot's Phase 1 research, identifying the major technical obstacles and studying whether credible solutions exist, that was officially declared complete. But the program went on hold in 2024, and public reporting since then has described it as largely stalled. Scientific American ran a cover story calling it a voyage to nowhere, though people closely involved with the project pushed back on that characterization, arguing the research phase genuinely succeeded on its own terms. What is clear is that the fully realized version of Starshot, laser arrays, fully functional gram-scale probes, actual flight to another star, remains extremely far from reality. Now let us talk about what many physicists consider the theoretical champion of interstellar propulsion ideas: antimatter. When matter meets antimatter, both annihilate completely, converting 100% of their combined mass directly into pure energy. This is the most efficient energy release physically possible. Einstein's famous equation, energy equals mass times the speed of light squared, applies here in its most extreme form. A single gram of antimatter colliding with a gram of ordinary matter releases energy equivalent to roughly 43,000 tons of TNT. The energy density is millions of times higher than chemical rockets, thousands of times higher than nuclear fission, and hundreds of times higher than fusion. In theory, an antimatter rocket could achieve a significant fraction of the speed of light with a far more manageable fuel mass than any other known propulsion method. In theory, it is the closest thing to a genuinely viable interstellar drive that physics allows. In practice, the entire global production of antimatter from every particle accelerator on Earth operating continuously for years amounts to a tiny, almost laughably small quantity. CERN, Europe's particle physics laboratory, and one of the most powerful accelerators ever built, produces anti-hydrogen atoms in experiments, but in quantities measured in nanograms, billionths of a gram. The energy required to create antimatter far exceeds the energy you get back from it, making current production methods hopelessly impractical as a fuel source. Storing it is a separate catastrophe, since antimatter annihilates instantly on contact with any ordinary matter container. And the cost? Estimates for producing even a single gram of antimatter using current technology have been calculated at roughly $62 trillion. 62 trillion. That is almost 3 times the annual GDP of the United States for 1 gram of fuel. And the amounts you would need for a real interstellar mission are not a gram. They are hundreds of thousands, potentially millions of kilograms. The gap between where we are and where we would need to be is not a step. It is not even a staircase. It is a cliff face so steep it disappears into the clouds. So where does this leave us? We have nuclear pulse propulsion, abandoned for political and safety reasons, and the physics was real, but the engineering was terrifying. We have nuclear fusion drives, theoretically powerful, but we have not yet achieved sustained fusion on Earth, let alone in a spacecraft engine. We have laser light sails, elegant and physically grounded, but burdened with engineering challenges so severe that the best funded effort to pursue them quietly ground to a halt. We have antimatter, theoretically perfect, practically impossible for any foreseeable civilization. And yet here is the thing. Every single one of these ideas represents something extraordinary. They represent the human mind refusing to accept the word impossible without at least examining it from every angle first. Every physicist who sat down and seriously calculated whether you could push a ship to the stars with nuclear bombs or laser beams or antimatter was performing an act of profound intellectual courage. They were saying that the universe's rules are real, and we are going to learn them so thoroughly that eventually somehow we find the path through. Science does not move in straight lines. It moves in lurches, in sudden leaps, in moments of insight that come from directions nobody expected. Right now, in 2026, we cannot see the technology that will eventually carry humanity to another star, if it ever exists. But then again, in 1903, the year the Wright brothers first flew at Kitty Hawk, nobody could see the technology that would carry a human being to the moon in 66 years. In 1945, nobody could see the internet. In 1973, nobody could see a pocket-sized device that would give every human being access to the sum total of human knowledge. The universe is vast. Our reach, right now, is tiny. But the distance between those two things has been shrinking, steadily, relentlessly, for as long as we have been asking questions about the sky above us. And the asking never stops. Up to this point, we have been talking about the universe as the obstacle. The distances, the physics, the energy requirements, all of it framed as the cosmos throwing up walls in front of us. But there is another layer to this story that is closer to home, much closer. Because the most fragile, most complicated, most unpredictable component of any deep space mission is not the engine, it is not the navigation system, it is not even the fuel, it is the human being sitting inside the ship. We are not built for space. We were engineered through billions of years of evolution for a very specific environment. We were shaped for one particular gravity, one particular mix of atmospheric gases, one particular level of radiation, one particular rhythm of day and night. Step outside of those conditions and the body starts sending distress signals almost immediately. Keep going further into deeper space for longer durations, and those signals escalate from discomfort into genuine danger and then into territory where our biology simply begins to fail in ways we are only beginning to fully understand. Let us start with the thing that is perhaps the most invisible and the most terrifying threat in deep space: radiation. Not the kind from a medical X-ray, which passes through you quickly and at relatively low doses. We are talking about galactic cosmic rays. These are subatomic particles, mostly protons and heavier atomic nuclei, that have been flung across the galaxy at close to the speed of light by the violent explosions of dying stars, by the shock waves of supernova remnants, and by the churning magnetic fields around black holes and neutron stars. They carry enormous amounts of energy, and they pass through almost anything. Here on Earth, we are protected from the worst of it by two overlapping shields. The first is our planet's magnetic field, which deflects many charged particles away before they can reach the surface. The second is our thick atmosphere, roughly the equivalent of 10 meters of water above your head, at all times, absorbing and scattering what gets through. Inside the heliosphere, the Sun's own magnetic field provides an additional outer layer of protection against galactic cosmic rays. We are, without realizing it, nested inside 3 different layers of shielding just by standing on the ground on an ordinary Tuesday afternoon. The moment you leave Earth's magnetic field, you lose the first 2 layers. The moment you leave the heliosphere, you lose the third. What remains is the raw interstellar radiation environment, and it is brutal. A 6-month mission to Mars with current technology would expose astronauts to roughly the same radiation dose that NASA currently considers a career limit for its astronauts. And that is just the transit, not counting the time on the Martian surface or the journey home. A mission to Mars and back using current propulsion systems would likely push astronauts well past the recommended career dose in a single trip. And Mars is still inside our solar system. It is still partly shielded by the heliosphere. It is, on the cosmic scale, practically next door. An interstellar journey lasting decades or centuries, even with advanced propulsion, would expose travelers to galactic cosmic rays at full intensity without any of the Sun's protection for the entire duration. These particles do not just give you a sunburn, they tear through DNA strands, they damage the lining of blood vessels, they increase lifetime cancer risk significantly. Peer-reviewed research published in 2025 in the journal Nature's NPJ Aging found that exposure to high-energy space radiation accelerates cellular aging. Specifically, it triggers a biological state in cells called senescence, where damaged cells stop dividing properly and begin releasing harmful chemicals that accelerate the aging of surrounding tissue. Essentially, deep space radiation does not just raise cancer risk, it may age you faster at the cellular level. Research published in Nature Reviews Neuroscience in 2025 found that galactic cosmic rays, particularly the heavy ions in that radiation, may impact the central nervous system in ways that are even more concerning than the cancer risk. Animal experiments, and we are still waiting on more comprehensive human data, suggest that exposure to heavy ions in space radiation can impair memory, reduce cognitive flexibility, and accelerate neurodegeneration. The brain, it turns out, may be particularly vulnerable to the specific types of radiation found in deep interstellar space. A crew member on a decades-long journey might arrive at their destination cognitively impaired, sharper memory gone, decision-making dulled, reaction times slowed. This is not a solvable problem with a simple engineering fix. Adding more shielding to a spacecraft helps against lower energy radiation and solar particle events, which are bursts of charged particles released during solar flares. But galactic cosmic rays are so energetic that thick shielding can actually make things worse, because when those particles slam into dense material like metal or water, they produce secondary showers of additional particles. The optimal shielding for galactic cosmic rays is still an area of active research, and there is no clear solution on the horizon that fully eliminates the risk for long-duration deep space travel. Then there is what microgravity does to the body. Without Earth's gravity constantly pulling on your skeleton, your bones stop receiving the mechanical stress signals that tell them to maintain their density. Bone mass loss in spaceflight has been documented extensively. Astronauts on the International Space Station typically lose about 1 to 2% of bone density per month in weight-bearing regions like the hip and lower spine, even with rigorous daily exercise regimes on board. Return them to Earth after 6 months, and they walk like people recovering from a serious illness, gradually coaxing their skeletons back to normal over months of rehabilitation. The current record for the longest continuous human spaceflight is 437 days, held by Russian cosmonaut Valery Polyakov, who spent that time on the Mir space station back in the mid-1990s. His return to Earth showed the toll that extended microgravity takes on the cardiovascular system, the muscles, and the bones, even with significant countermeasures in place. For a journey measured in years or decades, the bone and muscle atrophy problem is genuinely severe. Exercise can slow it, it cannot stop it entirely, and the human cardiovascular system, which evolved to pump blood upward against gravity, redistributes fluid when that gravity disappears. Fluid shifts toward the upper body and head, raising intracranial pressure. Recent studies of astronauts who spent extended time on the ISS found structural changes in their brains. The brain literally shifts position slightly inside the skull, and cerebrospinal fluid volumes change. Some of these changes persisted for up to a year after the astronauts returned to Earth. A 2025 review in Nature Review's Neuroscience confirmed these findings and highlighted that the full recovery trajectory after long-duration spaceflight remains incompletely understood. One elegant, though deeply complex, potential solution is artificial gravity. Spin the spacecraft, create centrifugal force, simulate the effect of gravity for the crew. This has been a staple of science fiction forever, and it is physically real. The physics works. But actually engineering a rotating habitat large enough to generate comfortable artificial gravity without causing motion sickness while managing all the other demands of an interstellar spacecraft is an enormous challenge that no mission has yet attempted. But now let us step away from the purely physical and talk about something that may be even more difficult to engineer around: the human mind. In 2011, a remarkable experiment concluded in Moscow, Russia. 6 volunteers, 3 Russians, 1 Frenchman, 1 Italian, 1 Chinese citizen, had spent 520 days locked inside a mock spacecraft at the Russian Academy of Sciences Institute of Biomedical Problems. The project was called Mars 500, and it was the most ambitious simulation of a long-duration space mission ever conducted on the ground. The facility simulated every aspect of the journey it could, including communication delays with ground control, isolation from the outside world, limited resources, and the confined quarters of a realistic spacecraft module. The results were published in scientific journals and were illuminating in ways both expected and unexpected. Over time, several of the crew members developed significantly disrupted sleep patterns. Some began sleeping dramatically more than usual, a response that researchers interpreted as a kind of psychological withdrawal, a way of mentally escaping the monotony and confinement. Physical activity levels dropped despite having the means to exercise. Cognitive performance testing showed measurable declines in some participants, and this was on the ground in Moscow. No actual radiation, no actual weightlessness, no actual awareness that there was no going back. Just confinement, isolation, monotony, and time. Now scale that up. Imagine the same psychological landscape but without the flaw being a Moscow research facility. Imagine knowing that Earth is so far behind you that it appears as nothing, not even a point of light visible to the naked eye. Imagine that any emergency, a medical crisis, an equipment failure, a psychological breakdown, cannot be solved with outside help, because outside help is years of travel time away. Imagine that if something goes catastrophically wrong, there is no rescue mission, there is no abort and return option. The journey is, in a very real and permanent sense, one way. The human mind did not evolve to process that reality. We are social animals, wired for community, for the presence of others we trust, for the sensation of open sky and changing seasons and the smell of rain. Deep space strips all of that away and replaces it with a metal tube, recycled air, artificial light, and the company of 3 or 4 other people for years without a moment alone. Research into the psychology of extreme isolation and confinement, from Antarctic winter overteams to submarine crews to space station inhabitants, consistently shows that long-duration confined groups face predictable challenges, interpersonal conflicts that escalate disproportionately, depression, anxiety, reduced motivation, cognitive dulling, and a phenomenon researchers call the third quarter effect, where morale drops sharply when a long mission passes its midpoint. The end feels still too far away to be encouraging, and the beginning is gone. There is also the profound, almost philosophical challenge of communication delay. On the International Space Station, astronauts can call home in real time, they can video chat with their families, follow the news, stay connected to the world they left. Even on a Mars mission, the communication delay would range from 3 minutes to 22 minutes each way, depending on orbital positions. Manageable. Frustrating, but manageable. On an interstellar journey, even to the nearest star, a message home would take over 4 years to arrive and another 4 to get a reply. Anything you say to someone you love is a letter sealed and sent into time. Their answer arrives 8 years later. By then, everything you asked about has changed. That is not just logistically difficult, it is existentially profound. You leave Earth, and every human connection you have becomes a kind of memory, a relationship with people who will age and change and eventually die while your message is still traveling through the dark. The people who launch you on your journey are not the people who will still be alive when you send back your first report of what you found. The grief of that is not a small thing. It is the kind of thing that reshapes who you are. And yet, and this is important, human beings have proven over and over again to be capable of extraordinary endurance in service of something they believe matters. The crews of the Mars 500 simulation came through it. Antarctic researchers endure months of near-total isolation in conditions that would break most people. The astronauts and cosmonauts who have spent a year or more on the space station come home changed, sometimes deeply, but still themselves, still curious, still laughing, still looking up. The human spirit is not a fragile thing. It bends, it strains, but it is remarkably often stronger than the conditions trying to break it. And that might be the most important finding from all of this research into what space does to us. We are not perfectly suited to the cosmos, but we are not entirely unsuited to it either. We are somewhere in between, which is perhaps exactly where the most interesting stories always happen. Let us pull back, way back, further than we have gone in this entire conversation. Let us stop thinking about rockets and radiation shielding and simulated Mars missions for a moment. Let us zoom out until our entire solar system, the Sun, all 8 planets, the Kuiper Belt, the Oort Cloud, the whole magnificent, terrifying structure we have been talking about, shrinks down to a single dot, a grain of sand on the longest beach you have ever seen. Because that is what our solar system is, in the context of the Milky Way. One star system among hundreds of billions. One quiet neighborhood in a galaxy so enormous that even the speed of light, the fastest anything can travel in this universe, takes roughly 100,000 years to cross it from edge to edge. Our galaxy is 100,000 light-years wide. If you somehow boarded a beam of light and rode it straight across the Milky Way, Everyone you had ever known would have been dead for 50,000 generations before you reached the other side. Here are the raw numbers because they deserve to be stated plainly. The Milky Way contains roughly 100 to 400 billion stars. Estimates vary as new data refines our models, but the order of magnitude is consistent and staggering. Recent research using more accurate counts of red giant stars, published in the journal Nature Astronomy, suggested the distribution may be somewhat different from older models, but the total count remains in the hundreds of billions. Most of those stars, it turns out, have planets. We have confirmed over 5,500 exoplanets as of the mid-2020s, and that number grows constantly as telescopes like the James Webb Space Telescope add to the catalogue. Statistical analysis of the data strongly suggests that on average, every star in the Milky Way has at least one planet, and many have several. That means the galaxy contains somewhere between hundreds of billions and over 1 trillion worlds. 1 trillion planets circling hundreds of billions of stars in a galaxy that has been around for roughly 13.6 billion years, almost as old as the universe itself, which formed about 13.8 billion years ago. Stars in the Milky Way formed long before our Sun ignited, which happened about 4.6 billion years ago. Many of those older stars had billions of years of head start, which means, statistically speaking, if life arises anywhere near as readily as it did on Earth, there should be civilizations out there that are millions or even billions of years more advanced than us. And yet, listen, do you hear that? Nothing. The sky is silent. Every radio telescope, every optical survey, every infrared scan we have ever pointed at the cosmos has come back with the same answer. Nothing confirmed, no alien signals, no megastructures around distant stars, no obvious signs of civilizations reshaping their planetary systems, no transmissions, no laser pulses, no traces of technology that cannot be explained by natural processes. Just stars and gas and radiation and the ancient hum of the cosmos going about its business, utterly indifferent to whether anyone is listening. This silence has a name. Scientists call it the Fermi paradox, after the Italian-American physicist Enrico Fermi, who reportedly asked the question at a lunch conversation with colleagues back in 1950. Where is everybody? Given the age and size of the galaxy, given the staggering number of worlds that should have had time to develop life and technology, where are all the aliens? The math seems to demand they exist. The sky insists they do not, or at least that they are not making themselves obvious. That contradiction, that gap between expectation and observation, is one of the deepest unsolved puzzles in all of science. There is no shortage of proposed answers. Some researchers argue that intelligent life is simply extraordinarily rare, that the specific sequence of events that produced life on Earth, and then complex life, and then intelligent life, and then technological civilization, is so improbable that it may have happened only a handful of times in the entire observable universe. This is sometimes called the rare Earth hypothesis, developed in detail by paleontologist Peter Ward and astronomer Joe Brownlee in their book of the same name. The argument is sobering. We sometimes assume that because it happened here, it must be easy. But the history of life on Earth includes near-extinction events, mass die-offs, cosmic bombardments, radical climate shifts, and astronomical luck that allowed the right conditions to persist for long enough for intelligence to evolve. There is no guarantee any of that is common. Others argue the opposite, that life probably arises easily, but that intelligence is the bottleneck. Simple microbial life might be scattered all across the galaxy, but the leap from single-celled organisms to complex multicellular life, and then to intelligence, might be extraordinarily rare. Life spent roughly 3 billion years on Earth as mostly single-celled organisms before complex life exploded in the Cambrian period. That is 3 billion years of just sitting there, being small and undifferentiated. If that gap is the norm across the galaxy, then even planets teeming with bacteria might be separated from technological civilization by timescales longer than stars live. And then there is the hypothesis that haunts most thoughtful people who think carefully about this problem. The idea that civilizations do arise, that they develop technology, that they reach for the stars, and then something stops them. Every one of them. Something so common and so catastrophic that no civilization ever makes it past a certain point. Researchers call this the Great Filter. It is either behind us, something in the past that was extraordinarily hard to get through, which we somehow managed, or it is ahead of us. A threshold that every civilization that reaches for the stars eventually hits and fails to cross. A paper published in the journal Acta Astronautica in 2024 raised a striking and genuinely unsettling version of this idea. The researcher, Michael Garrett from the University of Manchester, proposed that the rapid development of artificial intelligence, culminating in what he described as artificial superintelligence, might itself be the Great Filter. The idea is that every civilization that reaches a certain level of technological sophistication creates something smarter than itself within a very short window of time relative to the age of the universe, and that this transition is so unstable, so unpredictable, that most civilizations do not survive it. If the typical window between a civilization developing radio technology and creating artificial superintelligence is just a century or two, and if that transition tends to go catastrophically, then the galaxy could be full of civilizations that burned brightly and briefly, leaving nothing behind but the fading echo of a signal that crossed empty space for thousands of years, undetected. It is a chilling thought. And it is not presented here to frighten you, but to open something up. Because the Great Filter, whatever it is or wherever it sits on the timeline of civilizations, is deeply connected to the question at the heart of this video. Getting out of the solar system is not just an engineering challenge. It may be the defining test for any species that reaches the point of asking the question. Whether any civilization ever actually manages to send something, anything, meaningfully into the space between stars may be one of the rarest achievements the universe permits. The most recent massive CT search using data from the Very Large Array Radio Telescope and published in February 2025 surveyed a huge swath of the northern sky and found no confirmed alien signals. The Cosmic Project, a sophisticated automated pipeline designed to sift through enormous volumes of radio data and filter out human-made interference, returned a null result. Not a single transmission that could not be explained as either natural or human-made. Another paper published in early 2026 by researchers at EPFL in Switzerland used Bayesian statistical analysis to examine whether alien signals could have already reached Earth and gone undetected. Their conclusion? It is unlikely we have received clear, detectable signals that we simply missed. The silence, they argued, is probably real, not a gap in our listening, a gap in the shouting. Now, none of this proves there is no intelligent life elsewhere. Science does not work by proving negatives. The absence of evidence is not evidence of absence, as the saying goes. We have surveyed only a vanishingly small fraction of the galaxy's stars in a limited range of frequencies over a few decades, a blink of an eye compared to the timescales involved. There could be civilizations out there that are intentionally quiet, civilizations that use communication methods we have not imagined yet, civilizations that are so far away that their signals have not reached us, civilizations so advanced that we would not recognize their technology as technology, just as an ant would not recognize a smartphone as a tool. But the silence is there, and it speaks in its own way. Here is the most profound possibility, the one that keeps astrophysicists lying awake at 3 in the morning turning it over. What if the Fermi paradox is not a paradox at all? What if it is a data point? What if the silence of the cosmos is telling us directly and honestly that what we are attempting to do, to leave the solar system, to cross the interstellar void, to spread across the galaxy, is not a thing that gets done easily or regularly or perhaps at all. Our Milky Way is 100,000 light-years across. It has been around for 13.6 billion years. Even at the relatively slow pace of civilization spreading from star to star, hopping between neighboring systems over thousands of generations, a civilization that started just a few million years ago could theoretically have colonized the entire galaxy by now. If interstellar travel were feasible and common, the fact that we see no evidence of this, no Dyson spheres around distant stars, no signals, no great engineering projects visible from Earth, suggests that either the spreading does not happen, or the civilizations that attempt it do not survive long enough to spread very far. That is a sobering thought to hold. But here is the other side of it. Here is the part that fills you with something other than dread. We are asking the question, right now, in this moment, on this small rocky planet orbiting an unremarkable star in one of the outer spiral arms of an ordinary galaxy, a species that has only had writing for about 5,000 years is grappling seriously with the question of how to leave the solar system. We have built telescopes that can detect the atmosphere of a planet circling another star. We have sent probes into interstellar space. We are mapping the Milky Way with instruments of such precision that we have catalogued the positions and motions of over 170 million stars in a single study published just in March of 2025. We are young, we are small, we are cosmically insignificant by most measures, and we are trying anyway, with everything we have. Every generation someone looks up at the stars and asks how to get there. That has to count for something. In a silent galaxy, the asking itself might be one of the rarest things there is. Carl Sagan once wrote that the cosmos is within us, that we are made of star stuff, that we are a way for the universe to know itself. And I think about that when I consider the silence. Maybe the universe made us curious precisely because it needed something to look back at it. Maybe that is what we are for, not to conquer the stars, but to notice them, to measure them, to tell their story. To be, for however long we persist, the part of the universe that wonders. That is not a small thing. In a cosmos this vast and this old, wonder might be the rarest element of all. We have spent a lot of time talking about why the journey is so hard. The distances, the physics, the energy, the human biology, the silence of the cosmos. But let us flip the perspective for a moment. Let us talk about what is actually out there. Because the reason any of this matters, the reason generations of scientists and dreamers and engineers have been willing to face all of these staggering obstacles, is that the destinations are extraordinary. The universe beyond our solar system is not empty and boring. It is overflowing with worlds. And right now, thanks to the most powerful space observatory ever built, we are beginning to glimpse what some of those worlds actually look like up close for the very first time. We are living in a genuinely historic era of astronomy. The James Webb Space Telescope, launched on Christmas Day of 2021 and fully operational since the summer of 2022, has fundamentally changed what we can know about planets around other stars. For most of human history, exoplanets, worlds orbiting stars other than the Sun, existed only as theoretical possibilities. Then in the 1990s, we started detecting them indirectly through the tiny wobbles they cause in their parent stars, and through the tiny dips in starlight when they passed in front of their suns. By the mid-2020s, we had confirmed over 5,500 of them, but confirming a planet exists is very different from understanding what it is like. For decades, our knowledge of exoplanets was almost entirely reduced to a few measurements: how big they are, how much they weigh, how far they orbit from their star, and how long their year lasts. The Webb telescope changed that. It did something that was considered essentially impossible just a generation ago. It began reading the atmospheres of other worlds. By watching how starlight filters through a planet's atmosphere as the planet crosses in front of its star, Webb can detect specific chemical fingerprints, the spectral signatures of molecules like carbon dioxide, water vapor, methane, and others, and tell us what those distant skies are actually made of. That is not just fascinating science, that is one of the most profound capabilities humanity has ever developed. We are, for the first time, smelling the air of other worlds. Let us start with the destination that sits closest to home. Proxima Centauri b is a planet discovered in 2016 by a team of international scientists led by Dr. Guillem Anglada Escudé from the University of Barcelona. Using data from the European Southern Observatory's HARP spectrograph in Chile, it orbits Proxima Centauri, the closest star to our Sun, sitting at just 4.24 light-years away. And in some ways it has the profile of a world worth dreaming about. It is roughly Earth-sized, and it sits within what astronomers call the habitable zone, the range of orbital distances from a star where liquid water could theoretically exist on a planet's surface, given the right conditions. The problem with Proxima Centauri b, however, is that its star is not at all like ours. Proxima Centauri is a red dwarf, a small, dim, cool star that burns much more slowly and steadily than the Sun. And red dwarfs, for all their longevity, tend to be spectacularly violent in their youth and activity. They routinely blast out enormous flares of high-energy radiation and charged particles, the kind that would, if the planet has no strong magnetic field or substantial atmosphere, gradually strip away whatever protective layers it might have built up. Research using data from the James Webb Space Telescope, as well as modeling studies published in peer-reviewed journals, has explored how ozone chemistry in Proxima b's potential atmosphere might affect temperature and wind patterns, and whether an atmosphere could survive at all in the face of Proxima Centauri's persistent activity. The research, including a study from Hebrew University of Jerusalem published in 2024, described the work as a significant leap forward in understanding potentially habitable exoplanets. But crucially, and I want to be clear about this, no confirmed detection of a thick, protective atmosphere around Proxima Centauri b has been established. The planet remains a compelling candidate, a tantalizing possibility, not a confirmed ocean world or a proven haven for life. What we can say with confidence is that it is out there, 4.24 light-years away, the closest known potentially habitable real estate in the universe to our current knowledge. A world that might have liquid water or might be a scorched, stripped rock battered by stellar flares, or something stranger than either of those options. And right now, with the telescopes we have, we are getting closer to an answer. Then there is the system that has arguably generated more excitement among planetary scientists than any other discovery in the history of exoplanet research. 40 light-years from Earth, in the constellation Aquarius, orbits a tiny, dim red dwarf star called TRAPPIST-1. It was named after the transiting planets and planetesimals small telescope in Chile that first detected it. And when astronomers studied this system more carefully, what they found made the entire scientific community stop and catch its breath. Not one planet, not two, seven Earth-sized rocky planets, all orbiting the same small star in a compact, tightly packed system. 3 of them sit within the habitable zone. 3 potentially water-bearing worlds around a single nearby star, a system so well organized and so accessible to study that it has become the most intensely observed planetary system outside our own. The TRAPPIST-1 planets were first confirmed in 2017, and in the years since, the James Webb Space Telescope has been systematically studying them, trying to determine whether any of them have atmospheres and what those atmospheres might contain. The results so far have been a mix of sobering and genuinely intriguing. For the 3 innermost planets, TRAPPIST-1b, TRAPPIST-1c, and the habitable zone world TRAPPIST-1d, Webb's observations have ruled out the presence of thick, substantial atmospheres. Research published in Nature Astronomy in December of 2024 confirmed that TRAPPIST-1b likely has either no atmosphere or an extremely thin one, possibly a bare rock with certain surface characteristics. The same pattern emerged for TRAPPIST-1c, and TRAPPIST-1d. But the outer planets are a different, more hopeful story. A study led by researchers at MIT and published in September 2025 found that TRAPPIST-1e, one of the habitable zone planets, is unlikely to have a Venus-like or Mars-like atmosphere, which is scientifically interesting because it narrows the range of possibilities in a meaningful direction. And in December of 2025, astronomers using Webb published observations suggesting that TRAPPIST-1e might have something more surprising, hints of a Titan-like atmospheric signature. Saturn's moon Titan has a thick, nitrogen-rich atmosphere, unlike anything else in our solar system, and the suggestion that one of the TRAPPIST-1 planets might have something analogous was genuinely electrifying for researchers. More observations are needed, and the scientific community is being appropriately careful. These are early interpretations of difficult data, and extraordinary claims require extraordinary evidence. But the direction of the findings is genuinely intriguing. 40 light-years, that is the distance to TRAPPIST-1. In our everyday world, 40 light-years sounds close relative to the scale of the galaxy. In practical terms, at the speed of Voyager 1, it would take roughly 700,000 years to get there. Even at 10% of light speed, a speed we cannot remotely approach today, the journey would take 400 years. And yet, 40 light-years away, there is a system of 7 rocky worlds around a dim red star, and we are already beginning to read their atmospheric chemistry with a telescope floating in space near the Sun. That is extraordinary. That is one of the genuine triumphs of human curiosity and ingenuity. We cannot go there, but we are looking closely enough that we almost feel like we can. And it does not stop there. The James Webb Space Telescope has been rewriting the exoplanet catalogue almost every month. In January of 2026, scientists using Webb data confirmed the strongest evidence yet of an atmosphere around a rocky exoplanet called Toei 561b. It is described in scientific literature as resembling a wet lava ball, a world where the atmosphere may contain gases emitted by a magma ocean, a geological process so alien to our intuitions of what planets look like that it requires a moment to really absorb. Planets wrapped in oceans of molten rock, exhaling gases into space. Worlds so hot and so geologically active that they are perpetually volcanic across their entire surfaces. In late December of 2025, Webb also revealed what researchers at the University of Chicago described as one of the weirdest planets ever found. A Jupiter mass world orbiting a rapidly spinning neutron star, a collapsed stellar remnant the size of a city, in an orbit so tight that the planet completes a full year in under 8 hours. Its atmosphere is dominated not by hydrogen and helium, as most giant planets are, but by helium and carbon, with soot-like clouds and the theoretical possibility of diamond formations deep in its interior. Its gravity is so extreme that the planet itself is being stretched into a lemon shape by tidal forces. And no known theory of planetary formation can adequately explain how such an object exists. The universe keeps doing this. Every time we point our instruments at something new, we find something we did not predict. Something that challenges the models and forces us to rethink assumptions. Red dwarfs with compact systems of rocky worlds, lava planets with volcanic atmospheres, diamond worlds orbiting dead stars, worlds so hot that metals rain from the sky, worlds so cold that their atmospheres freeze and fall to the ground as snow when they pass through the far side of their orbits. And all of this diversity, all of this staggering variety of conditions and compositions and orbital configurations exists within a tiny bubble of our neighborhood in the Milky Way. Most of the known exoplanets orbit stars within a few thousand light-years of Earth. The galaxy stretches for 100,000 light-years. What waits beyond the reach of our telescopes in the vast, unexplored majority of our own galaxy is genuinely beyond our ability to imagine. Here is the thing that grips me most about all of this. When you look at the TRAPPIST-1 system, when you think about Proxima Centauri b, when you consider the sheer statistical likelihood that among the hundreds of billions of worlds in the Milky Way, there are places with oceans, with weather, with chemistry complex enough to border on biology, you are looking at addresses, real places with real coordinates in real space, places that have existed for billions of years while our planet slowly cooled and life slowly got complicated, and eventually, improbably, intelligent creatures started building telescopes and pointing them at the sky. Those places were always there, before we had names for them, before we knew stars were suns, before we understood that the faint smear of the Milky Way was made of 300 billion individual fires, each one potentially warming worlds of its own. They were out there then, and they are out there now, patient and indifferent and extraordinary. We just recently learned they exist and we cannot get to them. Not yet, not with anything we have. The distance between knowing they are there and actually standing on one of them is, for now, the full measure of the problem this video has been exploring, and it is a problem so vast and so real that it humbles every ambition we bring to it. But ambition, humbled, does not disappear. It just gets focused. We have talked about the physics, we have talked about the biology, we have talked about the silence of the galaxy and the worlds that wait beyond the reach of our fastest ships. Now it is time to talk about the most radical idea in all of interstellar travel. The one that does not try to solve the speed problem by going faster. The one that solves it instead by accepting completely and without flinching that the journey itself will become the destination, that the ship will become the world, and that the people who land on another star's planet will not be the people who left Earth. We are talking about generation ships, and the moment you seriously start thinking through what that actually means, things get complicated in ways that go far beyond engineering. The concept is simple enough on paper. If you cannot make the journey fast enough for a single human lifetime, you build a ship large enough and capable enough to sustain a community of people across multiple generations. The founders board the vessel and set off. They live and work and fall in love and raise children aboard the ship. Those children grow up knowing nothing but the inside of the vessel, with the stars visible only through viewports. They have their own children. Generations pass, the journey continues, and eventually, centuries later, people who share DNA with the original crew, but who are utterly different people, with different languages perhaps, different customs, different ways of understanding their place in the cosmos, step out onto soil that no human has ever touched. Soil orbiting a sun that is not ours. It is, in some ways, the most honest approach to the problem. It does not pretend that physics can be beaten. It simply restructures what a journey means. Instead of asking how to get a person across the void, it asks how to get a civilization across it. But when you dig into the actual requirements, the honest scale of what that takes becomes clear very quickly. Let us start with the numbers. A research paper published in the Journal of the British Interplanetary Society by French astrophysicist Frédéric Marin used a sophisticated Monte Carlo simulation tool called Heritage to calculate the minimum viable crew for a multi-generational journey to Proxima Centauri b. The simulation had to account for births, deaths, infertility rates, random accidents, genetic diversity, and inbreeding risk. What did the study find? A minimum of 98 people at launch is needed to ensure a 100% survival rate across a journey of roughly 6,300 years, which is the estimated travel time to Proxima Centauri b at 1% of the speed of light. 98 people. That is everyone in a small village. And the study was run under optimistic assumptions with strict social engineering rules in place. In more recent follow-up work published in 2025, Marin and colleagues explored how genetic mutations accumulate over multiple generations and what the phenotypic effects on the population might be over centuries of closed breeding. The findings underscore that managing a genetically healthy population in deep space is not just a numbers game. It involves sustained multi-generational discipline about who has children with whom and when. The social complexity of enforcing those constraints across centuries is almost impossible to overstate. Then there is the practical engineering side of the vessel itself. In late July of 2025, the Initiative for Interstellar Studies announced the winners of the Project Hyperion Design Competition, a landmark international challenge launched in late 2024 that brought together architects, engineers, anthropologists, and urban planners to design a conceptual generation ship. Teams from around the world submitted proposals judged on their ability to integrate architecture, engineering, and social science into a coherent, centuries-spanning habitat. The winning design was called Chrysalis. Picture something that stretches 36 miles in length, not meters, miles. It is conceived as a massive cylindrical vessel, rotating to generate artificial gravity for its inhabitants, powered by nuclear fusion reactors, and designed to house somewhere between about 1,000 and 2,400 people on a 400-year journey to Proxima Centauri b. The interior includes living quarters, food production spaces, schools, libraries, parks, warehouses, medical facilities, and communal areas. It is designed not as a spacecraft in the way we normally imagine one, a pressurized tin can with a few astronauts in sleeping bags, but as a city, a traveling civilization, a world unto itself that happens to also be a vehicle, and it is designed to be a one-way trip. The people who leave Earth on the Chrysalis will never come back. Their grandchildren will never come back. The voyage is permanent from the moment of departure. That is not a dramatic flourish. That is a literal engineering constraint because you would use the fuel for deceleration at the destination end, not for a return. Even the option of turning around mid-journey would require enormous propulsive energy and would still add centuries to the mission. Once you push off, you are committed in a way that no human endeavor in all of history has ever asked of anyone. That commitment opens up a philosophical abyss that engineers and ethicists have been circling for decades. And it is worth sitting with because it cuts to the deepest questions about what it means to be human and to choose for another. Consider the first generation. The people who board the Chrysalis on launch day are volunteers. They chose to leave. They understood as fully as any human mind can understand such a thing what they were giving up. Earth's open sky, their families, the warmth of sunlight that has been with their species for as long as species has meant anything. They made a decision. We might disagree with it, we might admire it, but it was their decision to make. Now consider the second generation, born on the ship midway through the journey. They did not choose this. They opened their eyes in a metal world of recycled air and artificial light, and were told that this was their life and this was their purpose, and the destination was 100 years away. They could not opt out. They could not emigrate. The universe outside the hull was instantly lethal and completely unreachable. In what sense did they consent to this existence? In what sense was their freedom intact? And what of the seventh generation, or the 12th? People separated from Earth by hundreds of years of elapsed time, by centuries of cultural drift, by the slow, inevitable divergence that any isolated population undergoes when cut off from the broader stream of a civilization. Are they still human in the way we mean it? Are they still the heirs of the project their founders began? Or are they something new? A people shaped entirely by the interior of a cylinder moving through the dark, with no real connection to the world that built the thing they live inside. These are not idle philosophical questions. They are among the most serious ethical challenges that any serious interstellar mission design must grapple with. Philosopher Tony Milligan, in his academic work on the ethics of generation ships, described the central dilemma as committing future humans to a life they did not choose, in a vessel they cannot escape, toward a destination whose value they had no say in deciding. The children born on the ship are born into a mission they inherited rather than chose. That creates a moral weight that no amount of thoughtful design fully resolves. And the social science challenges match the ethical ones in severity. The Project Hyperion competition specifically required teams to address knowledge transfer mechanisms. How do you ensure that the technical knowledge needed to maintain a 6,000-ton fusion-powered spacecraft across 400 years of continuous operation does not erode? How do you transmit engineering skills, medical knowledge, agricultural techniques, and mechanical expertise across 12 or 15 generations of people who have no external universities, no replacement experts to call in, no supply chain, and no margin for failure? What happens when the culture aboard the ship drifts away from the culture that built the mission? What happens when the great-great-grandchildren of the engineers no longer understand why certain things are done certain ways, only that they have always been done that way? History on Earth gives us sobering examples of what happens to isolated communities over centuries. Languages change, knowledge gets lost, beliefs shift, priorities evolve. A mission built around a specific destination and a specific purpose, sustained across centuries in complete isolation from the rest of humanity, is asking people not just to travel, but to become something new. Whether that something new would still be capable of completing the mission its founders set out to accomplish is an open question and a deeply uncomfortable one. And yet, there is something in the idea of a generation ship that stirs something very old and very deep in the human story, because in a real sense we have always been on one. Our species left East Africa roughly 100,000 years ago. We spread across the planet in waves of migration that took thousands of years. The people who walked across the land bridge into the Americas were not the same people who had set out from Africa generations earlier. The people who first sailed to the islands of the Pacific did not know what they would find. They loaded their canoes with everything they could carry, pushed off from shores they would never see again, and trusted that the ocean and the stars would take them somewhere worth going. Many of them died, some of them made it, and the places they reached became the homes of civilizations that shaped the human story for thousands of years afterward. Every great migration in human history has been, in miniature, a version of the generation ship problem. Every people who ever crossed a mountain range or a desert or an ocean in the hope of finding something better on the other side was committing not just themselves but their children and their grandchildren to a journey of uncertain outcome. They were making a bet on behalf of people who had not yet been born. We have always done this. It is not a new kind of courage, it is the oldest kind there is. The difference with an interstellar generation ship is the scale of the commitment and the completeness of the separation. There is no way to send a letter home, no way to resupply, no way to turn back, no way to maintain contact with the civilization that built you, that shaped you, that gave you language and mathematics and medicine. All of that must come with you, packed into the memory and skills and culture of a few thousand people, sealed into a metal world, hurtling through the dark between stars. That is terrifying, and it is magnificent. And it is right now in 2026, still entirely theoretical. We do not have the propulsion. We do not have the materials. We do not have the closed life support systems capable of sustaining a healthy ecosystem for centuries without resupply. We do not have the social science frameworks tested and proven enough to trust across that span of time, but we are thinking about it seriously, rigorously, with real teams of real scientists and real ethicists and real architects sitting around real tables and asking the hardest questions. That is how every enormous human achievement began, not with the technology, with the asking. And sometimes that is enough to start. We have spent 8 parts of this journey walking through walls. The wall of distance, the wall of physics, the wall of energy, the wall of the human body and the human mind, the wall of the galaxy's silence, And now, in the second to last leg of this story, it is time to ask the most forward-looking question of all. Is there any crack in those walls, any gap that physics actually permits, that some researcher in some laboratory has genuinely identified as a possible doorway through? Or are we simply admiring the walls forever, with no real hope of the other side? Let us take this carefully, because this is territory where honest science and wishful thinking tend to blur at the edges. There are ideas in this space that are genuinely worth discussing, and there are ideas that are firmly in the realm of speculation, dressed up in mathematical notation. The difference matters, and I will try to keep them clearly separated. Let us start with the concept that has captured the popular imagination more than almost any other in the physics of interstellar travel: the warp drive. Specifically the Alcubierre drive, first proposed by Mexican theoretical physicist Miguel Alcubierre in 1994. The idea is both elegant and deeply strange. Rather than trying to push a spacecraft to the speed of light, which, as we discussed, requires infinite energy and is therefore physically impossible, Alcubierre proposed warping the fabric of space-time itself around the ship. Compress space in front of the vessel, expand it behind, and the ship essentially surfs on a bubble of distorted space-time. The ship itself never moves faster than light within its local region of space, but the region of space it sits in moves, carrying the ship along, and in this way an observer watching from outside might see the vessel arrive at a distant point far faster than light could travel that same distance through flat, undistorted space. That is, at its core, the idea. And it does not violate special relativity because the ship itself is not moving faster than light locally. The space-time around it is doing the moving. It is a bit like standing on a moving walkway in an airport. You might only be walking at normal pace, but the belt beneath your feet carries you forward faster than your legs alone could manage. The problem, and it is a very large problem, is what it would actually take to create such a warp bubble. The original Alcubierre math required what physicists call exotic matter, a form of material with negative energy density. Nothing like this has ever been observed. We do not know if it exists in any useful, manipulable form. The energy requirements calculated for the original formulation were staggering beyond comprehension. Estimates put them at around 10 to the power of 62 joules for a bubble large enough to enclose a spacecraft. That number is so large it makes the total energy output of the Sun over its entire lifetime look like a birthday candle. Some calculations suggested it would require more negative energy than exists in the observable universe. For decades, this was where the conversation effectively stopped. Yes, general relativity mathematically permits warp drive spacetimes. No, we have no idea how to create the conditions required. The idea was fascinating as a thought experiment and useless as an engineering blueprint. But the conversation has not stayed stopped. In May of 2024, a team at the University of Alabama, Huntsville, published research describing what they called a first-of-its-kind physical warp drive model, one that they argued satisfies the energy conditions in certain configurations without requiring negative exotic matter. Lead researcher, Dr. Jared Fuchs, described the study as changing the conversation about warp drives, noting that by demonstrating a numerical model, the team had shown that warp drives might not be permanently relegated to science fiction. In December of 2025, Popular Mechanics covered new research building on these ideas, with headlines suggesting that a fully physically realized warp drive model had been developed that avoids the exotic matter problem. Now, I want to be clear and honest here, because this is exactly where the line between science and excitement gets easily blurred. These papers are genuinely interesting theoretical contributions. They explore whether the mathematical framework of warp drive spacetimes can be made more physically palatable. But they are still purely theoretical. They do not describe how to build anything. They do not eliminate all fundamental objections. They do not tell us where to get the energy or how to generate and control space-time curvature on demand, or whether the inside of a warp bubble would actually be navigable, or how you would steer it or turn it off at the destination. And most mainstream physicists remain very, very skeptical that any version of a warp drive will ever be technically realizable, even if the math can be made somewhat less objectionable as the space. Com headline put it in February of 2025. 30 years after warp drives were proposed, we still cannot make the math work to a satisfying degree. That remains an honest summary of the state of affairs. So where does the warp drive sit? It is a genuinely interesting theoretical territory. It has not been definitively ruled out by physics, but it is also not on any realistic engineering roadmap. It is, right now, a beautiful question wrapped in mathematics. Wormholes occupy a similar, though slightly different, position. The concept of a traversable wormhole, a tunnel through space-time connecting two distant regions, emerges from Einstein's theory of general relativity. The theoretical structures were first explored by Einstein himself and his colleague Nathan Rosen in 1935, which is why they are sometimes called Einstein-Rosen bridges. The question of whether such structures could actually be used as shortcuts through space has been a serious topic of theoretical physics for decades. Recent papers, including ones published in the European Physical Journal C in March of 2025 and in the Journal of High Energy Physics in April of that same year, continue to explore the mathematics of traversable wormholes under various theoretical conditions. Some of these constructions appear to allow traversability under specific frameworks of quantum gravity or particular matter configurations. A paper submitted to Archive in March 2025 by researchers from 3 institutions explored so-called ordinary wormholes arising from standard approximations in quantum gravity, meaning wormholes that do not require the exotic, highly special theoretical conditions that earlier constructions demanded. But the honest assessment remains what it has been for decades. Traversable wormholes, even if they can be shown to be mathematically consistent within certain theoretical frameworks, require conditions of curvature and energy that are far, far beyond anything we can produce or manipulate. They are cosmological structures, not engineering projects. And the question of whether they even exist naturally anywhere in the universe, let alone whether one could be found or created near Earth and held open long enough to be useful, has no satisfying answer yet. There is also the deep issue, often glossed over in popular accounts, of what happens inside a wormhole to an observer attempting to traverse it. General relativity does not guarantee that the interior of such a structure would be survivable, or even that it would remain open long enough for anything to pass through. The geometry of these things is unstable in most theoretical treatments. Threading them with matter tends to collapse them faster than any signal, let alone a spacecraft, could transit. So what then actually holds any realistic promise? Where, if anywhere, does the roadmap for genuine progress in deep space travel actually start? The most honest answer is closer to home than any of the spectacular options. The technologies that represent genuine, grounded, near to medium-term progress are not warp drives or wormholes. They are advances in propulsion that work within known physics, but push those limits much harder than anything we have deployed so far. Nuclear thermal propulsion is one of the most mature of these. Rather than burning chemical fuel, a nuclear thermal rocket uses a nuclear reactor to heat propellant to extreme temperatures, producing exhaust velocities roughly twice as high as the best chemical engines. NASA has been actively working on advanced nuclear thermal propulsion systems as part of its plans for human Mars exploration. Research published in the journal Acta Astronautica in September 2025 explored the centrifugal nuclear thermal rocket concept, which proposes using liquid rather than solid nuclear fuel to achieve specific impulses of around 1,800 seconds, dramatically better than chemical rockets. At those performance levels, round trips to Mars could be completed in roughly 420 days, and missions to the outer solar system and the Kuiper Belt become significantly more achievable. Nuclear thermal propulsion would not get us to another star, but it would extend our reach across the solar system in ways that create stepping stones and the habit of going further with each generation. Solar sailing, pushed to its most extreme theoretical form, also holds genuine promise as a pathway for uncrewed probes beyond the solar system. A paper from researchers at the Jet Propulsion Laboratory, published in early 2026, explored propulsion options for a mission to the solar gravitational lens focus, a point located roughly 650 astronomical units from the Sun, where the Sun's own gravity bends and amplifies light from distant objects, turning our star into a natural telescope of extraordinary power. To reach that distance in under 20 years would require speeds around 154 kilometers per second, achievable with an extremely lightweight solar sail performing a close perihelion pass near the Sun. This is not interstellar travel, but it is far deeper than anything we have achieved with Voyager. And developing the technology to reach 650 astronomical units in 20 years would represent a profound advancement toward the kind of velocities that begin to make the outer reaches of the Oort Cloud accessible within human careers rather than across geological ages. Perhaps most importantly, the near future of deep space exploration is not just about propulsion, it is about observation. The James Webb Space Telescope is already doing what was once considered impossible, reading the chemical signatures of worlds around other stars. The next generation of ground-based telescopes, including the extremely large telescope being built on Cerro Armazones in Chile, which will have a primary mirror nearly 40 meters across, will push that capability further still. By the time we have the technology to even contemplate sending a probe to another star, we may already know with extraordinary precision exactly what waits at the destination, whether the atmosphere is potentially breathable, whether liquid water exists on the surface, whether the biosignatures of life are present. That changes everything about the motivation and the urgency of the journey. If we can narrow down the target from hundreds of billions of worlds to a handful of confirmed, detailed, life-promising candidates, the case for investing the enormous resources needed to reach one of them becomes vastly more compelling. We would not be flying blind into the void. We would be navigating toward a known address with a known visitor's guide already in hand. And that is perhaps the most realistic shape of the path forward. Not a single dramatic leap, no warp drive announced tomorrow, no wormhole open next decade, but a steady, patient, generational accumulation of knowledge and capability, better propulsion, deeper probes, more powerful telescopes, smarter materials, closed life support systems that can sustain themselves for decades without resupply, AI systems sophisticated enough to manage long-duration autonomous missions without moment-to-moment human supervision, gene technologies that might allow human physiology to be made more resilient to radiation and prolonged microgravity, and through all of it, the gradual, painstaking reduction of the gap between where we are and where the stars are. None of this is fast, none of it is glamorous in the way that a warp drive announcement would be. It does not make for the kind of headline that sets the internet briefly on fire before the next thing takes over. But this is how humanity has always actually moved forward. Not in the leaps that the stories celebrate, but in the 10,000 smaller steps that made the leap possible. Newton was not born already knowing calculus. He stood on the shoulders of everyone who came before him. Every great journey in human history was paved by people who never saw the destination. The stars are waiting, and we are, one careful step at a time, learning how to walk in their direction. On the 14th of February 1990, a spacecraft named Voyager 1 turned its camera around. It had been traveling for over 12 years by then. It had passed Jupiter, photographed its moons up close for the first time. It had swept past Saturn, threading the outer solar system like a needle through the most beautiful fabric ever woven. And now it was far beyond Neptune, at the very edge of everything we had ever built or touched or sent, roughly 6 billion kilometers from the Sun. Its mission was effectively over. Its cameras were about to be shut off forever to save power for the instruments still gathering data. But Carl Sagan had argued persistently and for years that before the cameras went dark, the spacecraft should do one more thing: turn around, look back, take a photograph of Earth from the edge of the solar system. NASA had resisted. There were technical concerns about the cameras being damaged by the nearby sun. There were engineers who said the image would have no scientific value. They were right, of course, in the narrow sense. The photograph would not reveal anything new about our planet's geology or atmosphere or biology. It would simply show that Earth, from 6 billion kilometers away, was a single pale blue dot, barely a pixel, lost in a sunbeam, smaller than the head of a pin against the darkness of space. And that was precisely the point. The photograph was taken. Earth appeared in it as a tiny mote of blue light suspended in a diffuse band of scattered sunlight. Carl Sagan wrote about it in words that have since become some of the most quoted in the history of science. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. He went on. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. He wrote that in 1994, 32 years ago. And yet every single thing this video has explored across 9 chapters of fact and physics and human ambition confirms that he was right. There is right now, in 2026, nowhere else our species can go. The nearest star system is 4 light-years away and effectively unreachable with any technology we possess. The planets in our solar system are, in varying degrees, hostile to human life without extraordinary technological support. The galaxy is vast and silent and indifferent to our timelines, and yet here we are, still trying, still asking, still pointing telescopes at the dark. I want to use the last few minutes of this video to talk about what I think all of this actually means. Not the engineering, not the physics, but the meaning sitting underneath all of it that makes this the most important question our species is capable of asking. There is a phenomenon that astronauts sometimes describe when they first see Earth from space. Researchers have studied it extensively enough that it has a name: the overview effect. It is the sudden, visceral, often overwhelming recognition that our planet is a single, fragile, borderless object floating in the void. That the lines we draw on maps, the national borders, the zones of conflict, the categories that divide us from each other, are invisible from orbit. That from just a few hundred kilometers up, there is no them. There is only us, on a blue sphere, wrapped in a paper-thin atmosphere that is the only thing standing between every living thing that has ever existed and the absolute zero of space. Astronauts who experience the overview effect often describe it as the most profound moment of their lives. Some say it made them weep. Some say it permanently changed how they see every political argument, every war, every petty human conflict. From up there, the full absurdity of us failing to take care of the only home we have becomes impossible to ignore. From up there, the imperative of trying to understand this universe rather than just fighting over a corner of it becomes almost unbearably obvious. Now extrapolate that feeling to the scale we have been discussing in this video. Not a few 100 kilometers, not the moon, not Mars. The nearest star, the Milky Way. The observable universe, 13.8 billion light-years across, 14 billion years old, containing more galaxies than there are grains of sand on all the beaches of Earth. And on one rocky planet, orbiting one unremarkable star in one outer arm of one galaxy among hundreds of billions, a species that has existed for an eye blink of cosmic time, is building instruments to read the atmospheres of worlds around other suns, developing theoretical frameworks for bending space-time, designing ships that could carry civilization across centuries of void. That is extraordinary, not despite the difficulty, because of it. The fact that leaving the solar system is so hard is not a reason for despair. It is a measure of the scale of what we are attempting. If it were easy, it would mean the universe was small. The universe is not small. It is incomprehensibly vast, and it is ancient, and most of it is hostile to everything we are made of. And we are trying to understand it anyway, with our fragile bodies and our brief lives and our remarkable, irreducible curiosity. Think about what it has taken just to get to the point where we can have this conversation. Every civilization that contributed to human knowledge, every astronomer who charted the stars before electricity by candlelight, squinting through primitive lenses at points of light they would never reach, every mathematician who worked through the equations that became special relativity and quantum mechanics and the physics of nuclear fusion, every engineer who lost sleep over the trajectory calculations for Voyager 1, every astronaut who floated weightless and looked down at the Earth and came back changed, every scientist who pointed the James Webb Space Telescope at a tiny patch of sky that looked completely empty and found 10,000 galaxies where nothing visible had been before. We are the product of all of that work. We stand on top of it. And the only reasonable response to standing on top of a mountain that high is to look at the next one and start walking. The stars are not going anywhere. They will still be there in 100 years, in 1,000, in 1,000,000. The question is whether we will be, whether we will have kept the thread of curiosity alive through whatever challenges come between now and then. Whether the species that looked up at the night sky on some African savanna hundreds of thousands of years ago and wondered what those lights were will still be wondering, still asking, still reaching when the technology finally catches up to the ambition. There is no guarantee. History is not a story of inevitable progress. Civilizations collapse, knowledge gets lost, the thread can break, but it can also hold. It has held before through dark ages and plagues and wars, and every catastrophe our history has thrown at us. Something in us keeps asking, something in us keeps looking up, and that in the end is what this video is really about. Not the distances, staggering as they are, not the physics, humbling as it is, not even the silence of the galaxy, haunting as it remains. It is about the species that knows all of these things and knows how small it is, knows how far it has to go, knows how many of the obstacles may be insurmountable, and decides to try anyway because of all the things that define us, all the qualities that make us human. The one that has carried us furthest is not our strength or our speed or our numbers. It is our refusal to accept the horizon as a final answer. The universe is under no obligation to be reachable, but we are under no obligation to stop reaching. Look up tonight, pick a star, any star. Let yourself feel the full, unfiltered weight of how far away it is. 4 light years, 100 light years, 1,000. Let it be genuinely, uncomfortably vast. Do not look away from the scale and then notice that you are still looking, that you cannot stop looking, that something in you shaped by 4 billion years of life on this planet and 100,000 years of human wandering will not let you look away. That is the answer to all of it. Not a propulsion system, not a wormhole, not a warp drive, but that gaze, that refusal to stop wondering, that ancient, unkillable hunger to know what is out there. The solar system is, for now, the edge of everything we can reach, but it has never been the edge of everything we can imagine. And the space between those two things is where all of science lives. If this video made the cosmos feel both impossibly far away and somehow more personal, then you are exactly the kind of person who needs to watch the video on the screen. It is called "If We Could Travel at Light Speed, It Still Wouldn't Be Enough." If you thought the numbers in this video were humbling, just wait. Because we are about to find out that even the universe's own speed limit, the fastest anything can travel, the absolute ceiling that physics itself has written into reality, is laughably insufficient for the scale of what is out there. Click on it. I promise it will change how you see the sky tonight.